I decided to make an agenda. We're doing CSV import followed by path queries. So when we're talking about doing CSV imports, it's very similar to what we went over when we were talking about mapping the virtual graphs. The main difference is that only import is supported. So whereas with a virtual graph, you can either import the data from your relational data source explicitly into triples, or you can query it in place. CSV doesn't allow you to do the querying in place, which makes some amount of sense because it's a file. We'd have to be reaching into the file system, and that could get kind of obnoxious. You currently can't do the CSV import inside of Stardog Studio. I know they are currently working on that. For now, you have to go to the command line, so you'll see that a little bit when we do the live example later. And the old Stardog mapping syntax is also the only supported way to do a CSV import. I'm guessing that the SMS2, which is a lot nicer looking, and that's the format that I showed you guys when we did the virtual graph stuff, is forthcoming, especially because about once a week I ask the people responsible when that support's going to be coming, so if I just annoy them enough, they'll eventually put it in there for me. And then you guys will get to take advantage of it. All right, so when you're doing a CSV mapping, you use a turtle-like Stardog mapping syntax file to take your CSV rows and map them to a block of RDF. So you can see this looks a lot like Turtle. It basically is Turtle with a few minor tweaks. You use, so the CSV you're importing, I should probably start off by saying it has to have a header row at the top, which the vast majority of them are going to have that anyway, but just in case it doesn't, you would have to make one, because obviously you would need some way to specify which columns you're talking about. So you use those column headers, you surround them with curly braces like you see here, and you can use them in IRIs and literals. So if we have the one example here, I'm making an IRI called manufacturer-make, and I'm just using the value of whatever's in the make column. See if I can pop up. Yeah, so I had this little, I don't know how easily visible that is, but so we have this little CSV here about cars. So I can use the make, Ford, Chevy, whatever, in that IRI, and then I also am using it in the string label, so you can use it both places. And after the dash line there, that's just showing for the first row what that row will map to, so you see the turtle that you'll get out of it with both manufacturer dash Ford and Ford in the label. So sometimes, especially when you're making IRIs out of your column values, you can't necessarily guarantee that all of the characters in it will be URL friendly. So they could have a bunch, they could have like unencoded spaces or new line characters, or who knows what people can put into a CSV. So what you can do is use the little hash sign before your column name, and that'll take the SHA1 hash of the value. And so it'll guarantee that if you have anywhere you use that value, you'll get the same hash out of it, but it'll also guarantee that what you get will be IRI friendly and compatible. So in this case, I don't know if this had any examples of models. Yeah, so we have like a model here of Jeep Grand Cherokee. You can't really have spaces in URLs. So if we just use the hash there, we get model and then some gobbledygook that doesn't matter so much, because the human readable part of it is going to be the RDFS label, which is pretty easily read from there. The IRI is usually just read by machines, and they don't really care how hard it is to read. So again, you can see the mapping block at the top, and then what it becomes for that first row down at the bottom. there are a couple special variables that are specific to mapping CSVs, specifically row and UUID. So if I use underscore row underscore inside of my curly braces there, then it will just take the row number of the CSV and use that. So it's not unlike in like an Oracle auto int or any of those auto incrementing IDs. It's just a good way to, if you have a CSV representing like car sales or something, and each row is its own sale, then a pretty easy way to make a unique ID for each of those sales would just be to use the row number. So a quick example there. The UUID is another time if you need something to be unique, but you don't necessarily care what it is, because you'll be putting a label on it or something more human-friendly afterwards. You can use the UUID there, and that will just it'll generate a unique ID every time you use it. So, even if you use it like twice in the same block of your mapping, you'll get two separate IDs because it's guaranteed unique every time you do it. So if you need it to be unique but reusable at the same time, you can use a blank node. So the blank node syntax, I think the only syntax we had seen before it prior was using the square brackets, but you can also use the underscore prefix there. So in this case, I have something, some row that represents a specific price, and I might want to reuse that price later. So I can just make a price blank node, and then every time in my mapping that I use underscore colon price, it will use that same blank node identifier. So it's, again, guaranteed unique, but also reusable as you're going through the rest of your mapping. And this slide just says demo, so I'm going to move this out of the way. So we're going to take our cars.csv here. Let's see if I can keep that visible. And the mapping here, this specific mapping, this specific data set is all available in one of our GitHub repositories. So I can point you to that. It's called Stardog Examples versus the Stardog Training one. So we just have a big turtle file here. We have these 5 columns in our CSV. And so for each of the rows going forward, it will make RDF for this entire file. So the blocks that you get out of this one file, you'll see for each row. And as you can see, we're using row ID here. We're using kind of all of the things that we just went over. Fortunately, I have, actually, let me create a database first. We'll just call it cars. And so then I can go into my command prompt here. I've got the CSV and the turtle file, the mappings turtle file. So all I have to do is a Stardog admin virtual import. I specify the database name. I give it the mapping file, and then I give it the CSV file. Stardog goes to work, and then it says successfully imported 72 triples. So now, nope, that's not what I wanted to do. Where is my cars database? There it is. So if I just do a quick select star of what we have, as you can see, if we wanted to find this Jeep Grand Cherokee, for example, I know from my mapping that I should have Jeep as a manufacturer in here. So it should be manufacturer Jeep. So there we go. So we have our type of business entity here and the label. So again, just let's see if we have manufacturer. If I want to find the car here, I can search for a car that has the manufacturer. And there we go. So we found a car. So that would be the Grand Cherokee. So if we want to see what's in our data from that, we just have to do another query. Whoa, hello. There we go. So there's our Jeep Grand Cherokee. Now, so all of that, everything in the mapping file here was translated to RDF, which you can then query. You'll probably copy the prefixes over when you do so, and then it'll actually work right away for you, but you can see it's all in there. Were there any questions about CSV imports? Oh yeah, so the same kind of mappings here can be used to use on any of your Oracle SQL databases, or even things like Cassandra or Mongo, with a couple of tweaks. I don't think in any of those you can use these hash marks or the hashes. You can't use the row ID or the UUID. I guess with the row ID, you could probably fake it if you're passing it. You can pass in whatever the database specific row ID function is when you're using your SQL queries. But yeah, so it's a very similar sort of format when you're importing from a relational database. This one is very specific to CSV. Okay, so let me bring this over for like the 2 slides that I have before we go into more live demo. So we'll cover path queries. As we covered before, this is going to give you, by default, the shortest paths between any 2 nodes, which you can define or leave as variables, and using the given predicates. So I just kind of pasted in here the general. This is the normal form for a path query. So these show all the different keywords and sort of permutations of it. We'll go into some more detail and sort of add on the basic ones from here, but I just wanted to show the overall format right up front. And then have yet another live demo. What could possibly go wrong? So most of what we're going to see will be based off of this really simple graph. I think the graph that is in the live data is very slightly different. I think Charlie and David in that case are flipped. But still, you have these 5 people that are connected to each other by this predicate knows. There are also a couple other ones that are in the live data that aren't in here, but that shouldn't mess us up too badly. He said, okay, so let's head back here and we'll go to our very simplest path query. This is like the bare minimum of what you need to get things to work. So you say paths, start, give it a start variable, end, give it an end variable, and then via. And that's where you would give either the predicate or some way of binding S and E together. So when I run this, I will get, let's see, hold on a second, I had some notes up here. Yeah. So I'll get kind of what you saw in the graph there. I know that Alice knows Bob, so I can see Alice and Bob, and I can even click on this and see what P is bound to, in this case, knows. So the 22 results, because this is showing the shortest path from every node in our graph here to every other node in our graph. So Alice to Bob, to David, to Charlie, to Eve, and then so on and so forth. And you can see the bindings here because we have the variables in there to be bound, which I think was kind of the problem before when it wasn't showing anything. It's because the query that I was showing didn't actually find any. So you can specify your start or your end node here. If I just want to start with Alice, I can say S equals Alice, and then I'll only get these 4 results, starting with Alice and going to each of the other 4 nodes in the graph. Again, I could specify just David as my end, and that will give me these 4 from each of the 4 other ones to David. Or, of course, I can specify both of them. Then I'll just get the shortest path from Alice to David via any route here. So because we're not binding anything to the predicate, it can use any predicate, so it'll give you the shortest path there. If I want to, I could specify the predicate here. I could just say via nodes, and that'll be the same thing because these happen to be nodes. But if there's somebody like Eve here, Alice knows Bob and Alice knows one of these guys, but they don't know Eve. Eve knows David because the direction here matters. So if I tried to go from Alice to Eve via nodes, I'm not going to get any paths because that doesn't exist. But you can be a little bit more complex in your via clause here. So if you want to, you can say, you can use a property path. So nose or the inverse of nose. So this is basically nose in either direction. So then we can see it goes here. It doesn't really show that the direction goes from Eve to David in this particular case, but because we have that specified here. Studio isn't the only way to run these. You can also do it just on the command line, which some might like the formatting of that a little bit better. So if I just do a query of paths, and do that. So I get a little table. Let me just actually just put P back here. So we just get a little table, and so we can see that Alice knows Bob. Bob works with Charlie, and Charlie is the parent of Eve. So I guess those weren't in the graph that I showed, but they are in there nonetheless. That's a nice little way to show that. You can also tell it to use the text format, and it'll instead draw you a little version, kind of what's in Studio, except you don't have to click anything to see what the binding is, what the predicate is. So those are always two options. I know the path query support in Studio is always evolving. So we'll see, any enhancement requests are always welcomed. I do enjoy bugging the Studio people. So again, let's just go back to kind of this general. Actually, we'll go back to the very general thing. So again, the shortest paths by default let me Charlie. Okay, so well, either way. Oh, so yeah, that just shows the shortest by default. You can say paths all, and of course it doesn't have any. All right, we'll get one of these eventually. Okay, so, all right, if I say E equals David, we can filter out the other fluff. Again, if I didn't have all here, I would just get that shortest path. But here I've got kind of a roundabout path to get there, which you can also see the knows and works with and parent of, and then she knows David. So if I wanted to get all of the paths, you can do that. There's also a cyclical keyword. If you know that your path might have cycles in it, / you want to see if there are any cycles in your graph, you can use that keyword. Like it doesn't support infinitely going cycles, but it might point them out to you. So we also have a couple of keywords. Limit, like in a normal, your normal query. You can put a limit on that. You can also use a max length. So that'll get rid of that second one, even though we have all specified. So you can use limit and max length in conjunction with each other as well.